so let's start with Newton's law. Okay, so first law of motion. So what you can see here, if no external force, okay, so this is a typo error, this is supposed to be force. If no external force is acting on it, that means on an object will, if stationary, remain stationary, and if moving, keep moving at a steady speed in the same straight line. Okay, so there are two ideas over here. So if an object is in stationary, will remain in stationary. For example, if you put a book on a table, the book is in stationary, it remains stationary on the table until there is an external force that push the book, then it starts moving, or else it will just remain stationary. That is Newton's first law. And if you have a moving object, so the moving object here must be the object with no external force. So the best example that I can put is like the space shuttle in the outer space, so where there is no air resistance, so they will keep moving at a steady speed in the same straight line. So they will keep moving in straight lines where you can just turn on the engine to save petrol, so it will just keep moving. Okay, so that is first law. Now second law of motion is about F equal to ma. So this one we discussed a few times already, where I say F is the resultant force, okay, resultant force, and then m is the mass, a is the acceleration. So second law is about this formula, okay, this formula. So of course you may also see this second law of motion in words sometimes, in words. Okay, so let's take a look what kind of words that I mean here. Okay, so take a look. Newton's second law in words. So I put on a browser. Okay, Newton second law of motion. Okay, so where you can see it here, Newton's second law of motion can be formally stated as follow: the acceleration of an object as produced by a net force is directly proportional to the, okay, so let's see, proportional to the what? It's actually proportional to the mass, okay, proportional to the mass. So as you can see it, of course you have to click to see that, okay, so it's proportional to the mass. So acceleration is directly proportional to the mass. Okay, now let's see. Okay, so let me double check first. I think it's not proportional to the mass because the equation doesn't show to be correct. Okay, Newton second law of motion. Okay, so let's click this. Newton's second law of motion can be formally stated as follow: the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. So this should be the one under the second law. Acceleration is directly proportional to the net force, inversely proportional to the mass. Okay, so the equations will tell us this also. Okay, so let's see. You look at the equations. Acceleration equal to F over m. So since F is above, so acceleration is directly proportional to the net force. And m at the bottom, that means acceleration is inversely proportional to the mass. Okay, so that's the second law. Now we look at the third law. Third law of motion. If object A exerts a force on object B, then object B will exert an equal but opposite force on object A. So this is about actions and reactions. Okay, so if you have action on object B, then object B will exert a reactions on object A. So example will be, let's say, if you have an object on the ground, so the object will exert the weight on the ground, but the thing is the ground will exert a normal reactions on the object, and because of that the object will remain stationary on the ground. It doesn't sink all the way down to the bottom, so it will just remain there because there are forces that balance back with the weight. So there are action and reaction. So the action is the weight, the reaction is the normal reactions. So we have the third law. Okay, so we have first law, second law, and third law now. Okay, now let's just move on. Moment. So moment is related to circular motion, actually. It's related. So you see how. Moment, the unit is Newton meter, equal to force, which is in the unit of Newton, multiplied with distance from pivot, which is in the units of meter. So example, let's say we talk about the seesaw. Okay, so pivot is here. Okay, now if somebody sit here, okay, so let's say the weight is, let's say 500 Newton, and then the distance from here to here is 2 meter. And then you can count out the moment. So this is what we call the, when you count moment, right, we have to determine whether this is clockwise moment or anti-clockwise moment. So how we determine that? We take the pivot as the center, and imagine that this is the center of the clock. Okay, so if this is the center of the clock, then this direction is clockwise moment. Clockwise, so this is clockwise.
Pivot is like the center.
The center, of course, it's based on the center. You have to determine where is the center first. If the center is here, then you have to take the round shape.
Pivot
Yes.
is the center.
Sorry? What you mean by even if it's the center?
Is it like that? Does it mean that pivot is the center?
Yes, pivot is the center. You take pivot as the center of the clock. Then you will just imagine a circle in this way. So this is clockwise. Yeah. So clockwise moment. So if you want to count clockwise moment, then you just take the force 500 Newton multiply with the distance from pivot, which is 2, then you get 1000 Newton meter in the direction of clockwise. So that is where moment is a vector quantity. You see, they care about the direction, clockwise or anti-clockwise. Okay, in equilibrium, clockwise moment equal to anti-clockwise moment. Okay, so that means if you want to keep this seesaw in equilibrium, so the clockwise moment produced here, which is 1000 Newton meter, must be balanced off by the anti-clockwise moment. So how to balance out? Let's say I give another example. So let's say there are another guy here. Okay, so this guy is let's say 1.5 meter away from the pivot. Okay, so the thing is, what is the weight of this boy, let's say this boy, if he want to balance with the boy on the opposite side? So of course, in order to do this, we use clockwise moment equal to anti-clockwise moment. So clockwise moment equal to anti-clockwise moment. So clockwise moment is 1000, anti-clockwise moment is force multiplied with distance, and then you can count the W by dividing 1000 divided by 1.5, then you get 666.7 Newton. So you will get the weight of the boy. Okay, so based on the concept of equilibrium. Okay, so now let's see the next point. Increasing force or distance from the pivot increases the moment of a force. Okay, so let's say for example, you want to open the nut of a car tire. Okay, this is the car, let's say this is the car tire. Okay, so the car tire, there are nuts here. Okay, so you want to open the nut, so you have to use a spanner, for example. Okay, a spanner. Okay, so normally you find it very difficult to open it because basically the spanner, the normal spanner is a bit short. Okay, so because it's short, right, the distance from pivot is low in value. So that means from here, this is where the pivot stay, the pivot is here. So the distance, let's say your force is here. Okay, you're pressing it. So the force is here. The distance is here to here. Okay, so normally because the distance is too short, the moment is not big enough. Moments will make turning effect happen. Okay, so it is hard to open it. It's hard to open it because the distance is too short. So in order to make it easier to open it, so you can just increase the length. So for example, you put something to increase the length, and then you press here instead. Because the distance is now much longer, with the same force, the moments produced is much greater, and then the nuts can be loosened off. So you can open up the nut. Yeah.
So in order to like increase the moment of a force, we have to increase the force, or we can also increase the distance from the pivot.
Yes, correct. Increase the force or increase the distance.
Okay.
Yeah. Okay.
So that means you have to like use the spanner in a forceful way.
Yeah. That means you apply a stronger force. Yeah. Then you can make it open also. Okay. So if you feel like, oh, I'm not strong enough, and then you add something to the handle to make it longer, then you press it down, and then you will be able to open it.
Okay.
Yeah. Okay, now let's move on. Levers are force magnifiers. Okay, so turning a bow is far easier with a wrench because distance from pivot is massively increased, and so is the turning effect. Okay, so this is the concept that I explained just now, the nut. So you have to use a wrench or use a spanner to open it, and then it is easier because this is the lateral system. So where the distance from pivot is increased, and then the turning effect is increased also. That means the moment is increased. So this is what I mentioned just now. Okay. Now let's move on. We have the center of mass. Okay. Center of mass, imaginary point in a body where total mass of body seems to be acting. Okay. So let's say if you have an object, triangle objects. So you want to find the center of mass. So you have to do something like this. Okay, where you put a hole here, and then you hang the a string with a pendulum, a bob here. Okay, you put a bob here. So then you draw with a pencil the straight line of this. Okay, then after that you turn around, you hang your triangle at point B. Okay, at point B, that means this point B, right? You put at the hole here. Okay, you put on top here, and then you connect with the string again. Okay, so something like this. You imagine, and now you put your B on top. Okay, so then you connect with the string together with a load tip or a bob over there. So they call it plumb line. Okay, so after that you use pencil to draw a line. Okay, just now when you do it at point A, right, you also have a line already. Let's say the line is here at point A. So you already draw a line. Okay, so
So you must draw a line on the triangle itself.
Yes, draw on the triangle itself.
Okay.
So the intersection point of the two lines will be the center of mass. So this point is called the center of mass. So center of mass is a point where the total mass of body seems to be acting. So in other words, this is the point where the weight act. The weight act at this point, center of mass. Okay, so working out the center of mass. So let's see how. Mark 3 points on the edge of the cut. So 1 point, 2 points, and 3 points. So we need the third point to double confirm, So maybe you want to avoid mistake. So you see I put 2 points and I can decide the center of mass already. But for safety reason, it is good to mark 3 points. So which means what? You see, if I draw one more. Okay, now I hang the triangle at point C. Okay, so just now point A, I have a line already. And just now point B, I also have another line. Now point C, I repeat the same thing, I get another line here. So I can confirm the 3 lines intersect at this particular point. So this point is the center of mass. So that's why we use 3 points, just to play safe. Okay, so in fact 2 points is good enough, but 3 points will be the best. Okay, now make a hole using a pin on each point, hang it on a cork board, and make a line when it is stable. So I have to do something like this. Put a line and hang it with a load. Then these vertical lines you need to draw on the triangular paper, and then do this for all 3 points. Where all 3 lines intersect, this is the center of mass. So we can determine in this particular way. Okay. Yeah.
You have to draw the line on the triangle where the pendulum sticks.
Yes, correct.
But but you in order to draw the line, you have to like switch. Like first you put in A, then where the pendulum stays, then you have to draw a line there, and
Yeah,
then you
you draw
switch to
line.
B, and then is it like that?
Yes, correct. You switch to B, then you connect with the pendulum, and then you draw the line again.
Okay, sir.
Yeah. Then after that, you switch to C, connect with the pendulum, then draw the third line.
So don't have to like move the pendulum right so much, or you have to move the pendulum.
If you see this design, right, this pendulum you have to take out first, so that the cardboard can be taken out, or else it's blocking. You see, you can see that.
Mm-hmm.
Yeah, or else it's blocking. So that's why you have to take out the pendulum, and then take out the triangular cardboard, and then you change it to another hole. Then you put it back.
Also, you don't have to like move the pendulum to draw the line.
The pendulum will always a vertical line lah. That is the thing lah. Okay, so you just need to change it to different hole only.
Okay.
Yeah. Okay. Now, let's see the next subtopic. Stability. An object will be in stable equilibrium when it returns to its original position given a small displacement. Okay, so what are they saying is you displace the object, then after that it will go back to its original position, then that is what we call stable equilibrium. Okay, so for an object to start rotating, it needs to have an unbalanced moment about acting on it. Okay, so let's say I give you one example. Pendulum again. Okay, pendulum, which is like this originally. Okay, so now you have to give a small displacement. Okay, give a small displacement. So that means you just use your hand, hold the pendulum together with the bob, making an angle. Okay, making an angle, and then after that it will start rotating or oscillating. Okay, from here come here and then come here again. So at the end it will come back to the position here. So that is where it is in stable equilibrium at the end. Given that it is a small displacement, it cannot be too much. If it's too much, then after that the oscillation is not regular already. Okay, so it cannot be too much. So the displacement is a little bit, for example. Okay, so it cannot be too much.
So
Imagine.
that it has to go a little bit further in order to go back to its original position.
Yes, then it will oscillate. If let's say you put here too much, if you put here, so basically it won't oscillate one. You release your hand, then it will just fall down, and then after that, like moving up and down, shaking a bit, maybe they will oscillate afterwards. Okay, so that is not the normal oscillation already. Okay, so they also mentioned that for an object to start rotating, it needs to have an unbalanced moment. Unbalanced moment, that means clockwise moment or anti-clockwise moment. So that is unbalanced moment. How we know it is unbalanced moment? So there is a formula which you can consider also. You want to find out the net moment. You take clockwise moment minus with anti-clockwise moment. So if you minus and you get some value, then that means they are net moment. If they are net moment, we call it unbalanced moment, then the system will oscillate or will turn. Okay, will turn.
So the net moment is basically unbalanced moment.
Yeah, unbalanced moment. Yes.
So that's how to know that the system is oscillating.
Yeah, correct. So for example, like seesaw seesaw. So if there are net moment, then the seesaw will just move up and down, oscillate. Yeah. Okay. So same with swing also. So swing is more or less the same like this pendulum system. So the swing will swing because there is a net moment. Okay. So let's look at this then. The next subtopic, scalar and vectors. Okay. So a scalar or a scalar quantity is a quantity that only has the magnitude. So it can only be positive. So for example, speed. Speed is a scalar quantity. So besides speed, you can also take distance. Distance is also a scalar quantity. So no direction, only magnitude. A vector quantity has a direction as well as a magnitude. So for example, velocity. Vector quantity can be negative, can be positive or negative. Okay, so let's say
Displacement also vector quantity as well.
yes, displacement is vector quantity. Okay, so I give you some example for the important or the popular scalar quantity as well as the vector quantity. So the important example, first we have distance, displacement. Then we have the speed and the velocity. They are in pair, So after that we don't have already. So after that we have acceleration under vector quantity. We also have force. The force here include weight. Okay, so then energy is under scalar. So for example, kinetic energy, so that is under scalar quantity. So then we also have time. Time is scalar quantity. Okay, and so on. So these are the important one. Okay, now let's see. You see the example here. 11 km north, 11 km east. So you want to find out the resultant. So what we do is we just join up the two vectors. Vectors you can represent it by using a line with arrow. Okay, so first go up by 11 km north, then join up with 11 km east. So this is the starting point and this is the end point. So you draw a straight line to join up the starting point to the end point, and then you will get the displacement, in other words. This is the displacement. Displacement is where you look at the starting point and the end point, then you draw a straight line. That is the displacement. And you want to find the displacement, you use Pythagoras Theorem. 11 square plus 11 square equal to r square. Then just add it up. 121 plus 121 becomes 242. Then you square root, then you get 15 point something. Yeah. Okay, so this is what we call head to tail method. So head to tail method. Head to tail method is the head of the first arrow, which is here, join up with the tail of the second arrow. Okay, so basically this is the head. Join with the tail. of the second arrow. So head to tail method. So you join it up. So of course we have another method which is called parallelogram law, where you draw the first arrow 11 km north, then from the same point you draw the second arrow which is 11 km east. You see we don't use head to tail, we start from the same point. Then imagine this will form a parallelogram in this particular way. It's actually a square for this case. Then you draw a diagonal from the same starting point, and that is the resultant or the displacement. So this is the alternative way to find out the resultant. Okay, so we have done this part.
So it's like the horizontal line.
Yeah.
So you like mirror it the other side, and then you can find the Pythagoras theorem for one of the triangle of the parallelogram, like that, right?
Yeah, true. Okay. You can just shift it and use Pythagoras theorem. So it's similar idea lah, basically. Okay. Then now let us practice. For what we have learned so far, let's practice first. Okay, so let's see for this question. This question is about moment that we learned just now. Figure 3.1 shows a girl and a boy on a seesaw. So you see the boy is 1.6 meter from the pivot. The girl is 2.4 meter from the pivot. We know the weight of the girl, 300 Newton, but the weight of the boy is unknown. So the seesaw pivots on the log. Calculate the girl's moment about the pivot. So the girl's moment, we just take force time distance from pivot. So we write down the formula. Moment equal to force time distance. So writing down the formula, you get 1 mark. Then now you substitute value 300 Newton multiply with the distance 2.4, then you get 720 Newton meter. Okay, so this question is kind of direct actually, so we just use the formula directly. So we look at B now. The seesaw is balanced horizontally. Calculate the weight W of the boy. Okay, so we have to use the equilibrium concept, where the clockwise moment equal to
what do they mean, sir, when they say the seesaw is balanced horizontally?
That means the log here will remain, I mean it's not this log, okay, let's say I call this plank. The plank here will remain horizontal, not moving so not moving. Yeah.
Horizontal, isn't it straight from like the y-axis like that?
It's like the x-axis actually.
Oh, okay.
Yeah, horizontal will be like this. Okay, so that means there is no net moment. So clockwise moment equal to anti-clockwise.
So it's equilibrium.
Yeah, equilibrium. Okay. Then clockwise moment is for the boy. So the boy is W times 1.6. Anti-clockwise moment is for the girl. So the girl we already count 720. So you can count the W. 720 divided by 1.6. So we get 450 Newton. Okay, so that is how we handle it.
So
Yeah.
how do you know that the girl is anti-clockwise and the boy is clockwise?
So the way is you take the pivot as the center.
Okay.
Then after that, imagine this is like a clock. Okay, so imagine this is a clock. So the weight is acting down in this direction. So this direction, imagine, is like clockwise. Okay, so the boy is in clockwise. Whereas the girl, right, going down from this side, and imagine it turn this way. So this is like anti-clockwise. So you have to imagine it that way, taking pivot as the center of the clock.
Okay.
Yeah. So I call this anti-clockwise, and this one clockwise. Okay, so we have done these questions. Okay, for the question on page 16, we just need to look at C. This is related to what we learned just now, the scalar and vector quantities. Okay, let's look at the question first. Figure 1.1 shows a river in which the velocity of the flowing water is 0.85 meter per second, parallel to the river bank. So that means flow this way. Okay, this way, in horizontal. A swimmer set off from one bank. The velocity of the swimmer relative to the water is 1.2 meter per second at 45 degree to the river bank, as shown in figure 1.1. So that means the swimmer swim in this direction, 45 degree, swim in this direction. In the space below, draw a scale drawing to determine the resultant velocity of the swimmer relative to the river bank. This velocity is the resultant of the two velocities shown on figure 1.1. Label this resultant on your diagram. Okay, so there are a few things to do here. Okay, so let's do it one by one. Okay, first they ask you to draw a scale diagram. So you have two vectors. Okay, you have two vectors. This is the first, this is the second, let's say. Okay, now we have to draw out. Draw out, let's say I use head to tail method. Okay, so I set up my scale 1 cm, 0.2 meter per second. Okay, so in that case, for this 1.2 meter per second, 1.2, which is 6 times of this, so 6 times of this will be 6 cm. So I have to draw 6 cm at 45 degree from the horizontal. So what to do is you have to use protractor to help you. Draw 6 cm, measure 45 degree. Okay, so then you label this 1.2 meter per second. So I put a remark here, this is 6 cm. 6 cm, and you have to measure 45 degree by using protractor. Okay, now after that, after you drew 6 cm, then the next one is from the head of this arrow, you have to join up with the second vector, which is the velocity of water. So you have to draw the velocity of water, so which is 0.85, right? 0.85. Okay, so 0.85, that means imagine 1 cm represents 0.2. 0.85 is how many cm? So you divide. Where you take 0.85 divide by 0.2, then you get 4.25. Okay, so you have to draw out a horizontal line 4.25 cm. (0.85 meters per second). This is 4.25 cm. 4.25 cm. Okay, so after drawing this, now you can get the resultant. The resultant is where you look at the starting and the end point. So you just draw that. So this is the resultant. We call this resultant velocity. So how long is your resultant velocity? You have to use ruler to measure that. You use ruler to measure it, and yeah.
Use Pythagoras Theorem.
You use Pythagoras Theorem if it is a right angle triangle. Yeah. So of course, from what I did here, I realized that this is actually a right angle triangle. Yeah, it's true. It's a right angle triangle from what I did, where I drew it accurately, and then I realized that this is a right angle triangle. Okay. And I go and measure the length of the blue line, so I will get 4.25 cm also.
So it's like, is it still a Pythagoras Theorem? I mean, is it still a right angle triangle?
Yes, it's a right angle triangle. You imagine this is an isosceles triangle in this particular way, where here and here same. Then since here is 45, 90, so it's still suitable to use Pythagoras Theorem to, but the thing is, the question never expect us to use Pythagoras Theorem. They ask you to draw a scale diagram. So you just draw, and then you measure 4.25 cm, and then 4.25 cm is 0.85 meters per second. We get the resultant. So because of that, the resultant velocity is 0.85 meters per second, and because this is velocity, velocity has magnitude. 0.85 is the magnitude. It has also the direction. Okay, so the directions, of course, you can just measure it from here to here. Use protractor, you get 90 degree. Okay, so then you just set it up in this way, 90 degree to the river bank.
So can you repeat how did you get 90 degrees?
Imagine you are using protractor. You measure from this horizontal line. Okay, from here, this horizontal line, you measure to here, to the resultant velocity arrow, and then you get a 90 degree. Yeah, by measuring you will know. Okay. Yeah, then we get. Okay, so this one is settled already.